So what mathematicians have discovered is what happens if we do the compounding continuously. So I can take my n times per year and just start increasing n. So I look at quarterly, then I look at monthly, then I look at weekly, then I look at daily, then I look at hourly, then I look at minutely. And there is a point where the amount of extra you get is very infinitesimally small, which means that that is approaching a constant value. So instead of having to do that ugly calculation, we can actually simplify it down to this formula. So it turns out that infinite continuous compounding becomes this number E, which is 2.71828. So it's a naturally occurring constant, and it pops up all over the place. It's also in radioactive decay, so you might remember using it in like nuclear part of chemistry, like carbon dating kind of questions. Okay, so on your calculator, there will be a little E caret button. If you don't see it, look for the ln button. That's natural log. And then the shift on that is usually the E caret. Now, for me, if I do E caret on the typing, it doesn't work. So I'm going to have to type the number in. But if we had $100 and we're going to continuously compound it. So we put the 2.71828. We're going to raise that to, and then here it's not NT because the N is continuous, it's the rate, the APR times T, the number of years. So the APR for ours here is 8%, so 0.08 times, and then they said 10 years. So we would have $222.55 after 10 years. All right, so not too much, but we invested $100, so. Now, if it was 10,000 bucks, that would grow to 22,000. Yeah, it more than doubled our investment. That's a sizable amount. Now let's see what this one's asking. So let's say we've got 1,500 and we look at a 5% continuous compounding. And we're going to see how much will it have after 15 years. What if instead you did quarterly compounding? So we're just going to compare and contrast the difference between this continuous and quarterly. And they're choosing quarterly because if you did monthly, it's not that much of a change, which is why credit card companies and loans do monthly. Sort of. Like they say that, but if you pay off your account, you have to call in. FYI. I learned that the hard way. Because it's not whatever your remaining balance is, it's your remaining balance plus, and then they calculate the interest for the days. Jerks. So continuous 2.71828 to the, now our interest rate is 0.05 times 15 years. All right, so that will more than double. $3,175 and change. Now let's see what happens if we do it quarterly instead. So we still have the 1,500. Now instead of the 2.718, I'm going to put in my 1 plus my interest rate 0.05 split 4 times a year for the quarterly. And then this is going to get raised to the 4 times per year times 15 years. 3160.772. $15 difference. The continuous, like it is a tiny bit more money, But then when someone wants to pay it off, it does, like, it's weird because, all right, how much do I pay? This. And then when you go to pay, well, technically it's a tiny bit more now. So that's why daily is usually about the most you'll see for normal type loans. All right. I love how they talk about investment like we have money to invest. All right, so how much would you need to deposit into an account today to have $6,000 in 8 years? Suppose quarterly compounding and an APR of 4%. All right. So we want to know what our principal is. So that is our unknown. So I'm going to fill out some of these variables to the side so that P is our unknown. Our final amount is that 6,000 they told us. Our number of years is going to be 8. And the APR is going to be, I'll just go ahead and write 0.04. And then we are doing quarterly compounding, so that N is 4. All right. So what we're going to see here, I'm going to use P for the unknown. So we're going to have 6,000 over here. Then our unknown P times 1 plus 0.04, 4 times per year divided by 4, raised to the 4 times per year times 8 years. Okay, so this is the equation we would have. I need to crunch what this number is. So that is 1.3749. So now this formula I can instead say is 6,000 equals P times 1.3749. So now the question is, what number do I have to multiply times 1.3749 to equal to 6,000? Well, I could sit here and try numbers and guess and check, or I can take 6,000 and do the opposite of multiply, divide, and figure out what P is. So P here is going to equal 6,000 divided by 1.3749. Normally they'll give you rounding directions. If they don't, either go with dollars or cents. I'd try cents first if they don't tell you. So this would be $4,363.95. That's what I'd have to invest to have $6,000 in 8 years. I mean, you could technically say round it up to 96, because if we stopped at 95, we would actually be a tiny bit shy of 6,000 at the end of 8 years. But I don't know which way Alex will ask this or want it, so just try it out. And if it gives you a lot of issues, email me. I can go in and figure out what it wanted and beat it up. All right. So how much would you need to deposit into an account today to have $35,000 in 20 years? This is so cute. They think we're still going to have accounts in 20 years. Suppose quarterly compounding and an APR of 7%. Okay. So again, our same kind of setup. So we're going to have that equation set up. So this is if I got 35,000 that I want to have, my unknown principal, and then 1 plus 0.07 over 4 raised to the 4 times 20. So we figure out what that number is, and then we're going to do 35,000 divided by that number. So now I will go ahead and type 1 plus 0.07 per 4 times a year to the 4 times 20. All right, so 4.0064. Now we're going to do 35,000 divided by that crazy number. So we need to deposit $8,736 to end up with 35,000. Now I've heard tell something like, if you want to live off your retirement, you need to have like $1 million. So yeah. How much would you need to deposit into an account today to have 15,000 in 10 years with quarterly compounding and an APR of 5%? So let's calculate our 1 plus 5%, 0.05, quarterly compounding 4 times a year, raised to the 4 times per year over 10 years. All right, so we need to divide 15,000 by that decimal. So $9,126.31 would give us 15,000 in 10 years with those conditions. Yeah, Mathland, wee! All right. So there's how compound interest works, how those formulas work. If you did these in the past, they may have started to talk about logarithms and using log here. We're not going to do that. So this will be the way it is, where it asks you, what's the initial investment you need to get this at the end? That is how the question will get asked. Or the straight up, I have this and here's the conditions, what will I have at the end? Alrighty.